In the third and final part of our three-part exploration of the solar system, we now turn to the small icy and rocky bodies. The trans-Neptunian objects are a numerous class of small icy bodies that orbit beyond the orbit of Neptune, as suggested by their name, trans-Neptunian objects. These objects are composed mostly of ices, with very low density between about 1.2 and 2 grams per cubic centimeter. Those objects on the high end of this density range, about 2 grams per cubic centimeter, are telling us that they're composed of a mixture of ice and rock. These consist of the icy dwarf planets Pluto, Eris, Haumea, and Makemake, and a larger class of very tiny, often irregular objects called the Kuiper Belt objects, which lie in a distinct band of objects between 30 and 50 astronomical units from the Sun. They also include among their number Pluto's very large moon Charon, and distant and icy outer bodies like the candidate dwarf planets Sedna and Quaoar. The picture on the right on the screen shows in red the orbits of the currently known trans-Neptunian objects. We know of many thousands of these now, but they're very difficult to observe because they're small and they're situated very far from the Sun in the outer reaches of the solar system. The outermost circle that is drawn on this plot is the circle of the orbit of Neptune. The largest known trans-Neptunian objects are the 4 dwarf planets of the outer solar system: Pluto, which has a retinue of, at current, known 5 moons, the large moon Charon, and the smaller moons Styx, Nix, Kerberos, and Hydra. Eris, the next largest of the trans-Neptunian objects, was once a candidate to be the 10th planet in the solar system. It has a small moon named Dysnomia. Dysnomia's orbit tells us that Eris is in fact a little bit more massive than Pluto, even if Pluto is slightly larger in radius. This is because Pluto is composed of more ices and is lower density. However, Pluto's mass is less than the mass of Eris, and so it qualifies as the least massive of the outer trans-Neptunian objects, even if it is the largest in radius. These are followed by Makemake and Haumea. The size of Makemake is largely guessed at by properties, how shiny it is and its spectral properties, because at present we do not know of any moons around Makemake. Haumea, on the other hand, is orbited by 2 moons, Namaka and Hi'iaka, whose orbits give us a very good mass for Haumea. You'll notice Haumea is irregular in shape. It's almost like a football or a rugby ball. We don't know the reasons for this, but it appears to be tumbling end over end, and it has very shiny ices. Perhaps Haumea is actually the reassembly of debris from an object that was disrupted by a large impact at some point in its history. And indeed, there are a number of smaller trans-Neptunian objects whose orbits plausibly remember something of the parent object that formed Haumea. They form a dynamical group. The other large trans-Neptunian objects include the most distant object we've ever clearly identified in the solar system, Sedna, 2007 OR10, Quaoar, and Orcus. These 4 objects are candidates to be dwarf planets, but we do not yet have enough information to know if they meet all of the characteristics. Quaoar and Orcus both have tiny moons, named Weywot and Vanth, respectively. Many of the names of large trans-Neptunian objects are named for various creation gods from the mythologies of peoples from around the world, from the Pacific Rim, from Native Americans, and so forth. Some of these names are getting a little bit difficult to assign because there are so many of these objects out there, it's difficult to make up new names for them. All the mythologies of the world are soon going to run out because the trans-Neptunian space may be very full of objects indeed. Asteroids are rocky or rock and metal aggregates found mainly in the main belt between Mars and Jupiter. These include objects like 253 Matilda, 651 Gaspra, and 243 Ida. These were all visited by the Galileo spacecraft en route to Jupiter. They are made primarily of rock and metal, but some of them are starting to be found that have large amounts of ice in their content. For example, they have densities between 2 and 3 grams per cubic centimeter, indicating that they're not purely rock, but have some admixture of ices within them. They range in size from a few hundred kilometers down to sizes of large boulders, maybe a few meters across. Well, there seem to be very numerous. If you took all of the asteroids, if you could somehow sweep up all of the rocks in the space between Jupiter and Mars and bash them all together, you would only end up with a tiny fraction of the total mass of the Moon. And so, while it sometimes was thought that the asteroids might have been a disrupted or broken up planet, there's not enough material to have made up an entire planet. In fact, there's barely enough material to make up a relatively small moon of one of the giant outer planets. The largest of the asteroids is Vesta. The dwarf planet Ceres is also in the main belt, but it's now classified separately as a dwarf planet and not as an asteroid itself. Vesta seems to land somewhat on the cusp between a large asteroid and a dwarf planet, and indeed there's quite a bit of argument over whether Vesta should be reclassified as a dwarf planet or not. That argument has not yet been resolved. Vesta was visited by the Dawn spacecraft, which went into orbit around it for a couple of years before firing its ion engines and heading off to Ceres, where it is located today. It returned a vast amount of information about this fascinating world, showing it pockmarked with craters, some unusual grooved terrain. Vesta is not perfectly spherical. It's actually got kind of an oblong shape, and this beautiful rotation movie shows the tremendously varied terrain. These objects in recent years have gone from points of light in the nighttime sky to unique and individual worlds all their own. The exploration of our solar system is continuing, and the more we look, the more we learn, the more we're finding out what a wonderful place our solar system is. This is a diagram showing the location of most of the main belt and some of the different families of asteroids that are found in the space between Jupiter and Mars. This picture is exaggerated. The asteroids really aren't these colors and certainly aren't this bright. And we've had to make these points big enough just to fill in the pixels so we could see them. This gives the impression that the space between Mars and Jupiter is somehow an obstacle course of spinning rocks. Nothing could be further from the case. For example, imagine that a typical size asteroid of maybe tens of kilometers across, or 1 kilometer across, let's pick 1 kilometer. Imagine that 1 kilometer is a pretty typical size for an asteroid, and imagine we scaled that down to the size of a typical Idaho potato. You could hold it in your hand. Where would the next kilometer-size asteroid be located, modeled as a potato? Would it be across the room? Right next door? Maybe down the street? Well, if you were in Columbus, Ohio, to go find, on average, the next kilometer-sized potato model asteroid, you would have to get into an airplane and fly to Minneapolis, Minnesota. The asteroid belt is actually pretty empty as far as places in space are concerned, and it's easy to fly spacecraft through the asteroid belt without any danger of hitting anything. We've mapped out most of the large bodies in the asteroid belt and seem to know where everything is, and in fact, people have redirected some spacecraft going through the asteroid belt to be able to get a close look. The Galileo spacecraft, sent from Earth to go orbit Jupiter many years ago, was redirected to look at some of the asteroids as it flew out to Jupiter, but at no time was it in any danger of running into a large object. That view of asteroid fields from movies like Star Wars, where spacecraft fly around, they're all very exciting, but they don't exist in our solar system. In addition to the asteroids, the meteors are tiny, small bits of rock and metal that range in size from grains of sand up to the size of boulders. Their compositions are threefold. There are stony meteors that are made mostly of silicates, and there are iron meteors made mostly of iron. Finally, there are the chondrites. The chondrites are the most interesting of the meteors in many ways because of their extremely high carbon content and the fact that we find throughout them a large number of organic carbon compounds, including amino acids. Amino acids, in particular the left-handed versions, are among the essential ingredients of life on the Earth. All of the proteins that are in your body and in all other forms of life on the Earth are made up of combinations, long chains, of different left-handed amino acids. However, chondrites have a mix of left and right-hand amino acids, like this little piece of the Murchison meteor here, and this is giving us some idea of how some of the complex organics are found in our universe. They aren't formed on the surfaces of planets. They may be formed out in the cold clouds of molecular material that we're going to find throughout interstellar space. The meteors are the leftover bits of rocky debris from the formation of the solar system. The fact that some are silicate and some are iron suggests that perhaps at one time these may have been part of larger asteroids that heated up and melted, and the material inside of them differentiated. The iron and nickel sinking to the bottom, and the silicates, which are lighter, floating to the top. However, shortly after this material solidified, the parent body had an enormous impact with another object in the asteroid belt and broke into pieces, freezing into place the composition from the differentiation of silicates and iron. What's the difference between a meteor, a meteorite, and a meteoroid? Good question. It's a meteor when it enters the Earth's atmosphere. It's a meteorite when it hits the surface, and it's a meteoroid when it's still out orbiting around the sun. And indeed, the parent bodies of the meteors are orbiting the sun. They probably come primarily from the main belt and the group of asteroids found between the orbits of Mars and Jupiter. When they enter our atmosphere, they get heated by friction passing through the dense air, begin to ablate and glow hot, and this gives us the bright streak that we see as a meteor. If it survives its passage through the atmosphere and falls to the ground as a rock we can pick up, they're called meteorites. Finally, in this general theme of debris of the solar system, we come to the beautiful objects, the comets. Comets are low-density composites of rock and ice. We used to call them dirty snowballs, but now it's pretty clear from a close study from spacecraft that comets are really dirty snow and mud balls. They're actually far more complicated than we originally thought. When they get close to the sunlight heats them up, and the frozen gases on their surface begin to stream off, carrying off little bits of silicate dust, forming these long, beautiful tails. It's tempting to think of the comet as this enormous object here, but indeed this is a bit of an illusion. Almost all the mass of the comet is way, way down inside in an object maybe only a couple of kilometers across, and very, very dark, like this close-up of Comet P67 Churyumov-Gerasimenko, taken from the Rosetta spacecraft. Comets are little, dark, dirty nuggets of ices and silicates from the outer solar system. When they plunge into the middle and they form these beautiful gas tails and comas, they look spectacular. But they're pretty empty. They're actually about as close to nothing as something can be and still be something. They originate primarily in the outer solar system. Their orbits bear the marks of their point of origin, either in the Kuiper Belt, a band of icy objects between 30 and 50 astronomical units found just outside the orbit of Neptune, or in the Oort cloud, a vast, nearly spherical cloud of the leftover frozen debris from the formation of our solar system that may extend as far out as 10,000 astronomical units. They develop these long tails of gas and dust swept off them by sunlight when they pass near the sun. And indeed, it's the appearance of the comets in the sky that is one of the most spectacular astronomical phenomena of the inner solar system. In the last couple of years, we've gotten a very up-close and beautiful view of one of these comets, called Comet P67 Churyumov-Gerasimenko, which is being visited and orbited by the Rosetta spacecraft, launched by the European Space Agency. These beautiful pictures show us that the comets, in addition to their manifestations as bright-tailed objects in the sky that occasionally appear, swing around the sun, and then vanish into the coldest space, are, on close inspection, individual and wonderful worlds all by themselves. And they are worlds that we have landed robotic probes on. In November of 2014, the tiny Philae lander no bigger than a small washing machine, was detached from the Rosetta spacecraft and made a somewhat bumpy, bouncy landing on the surface of Comet Churyumov-Gerasimenko. It actually fell into a dark crevasse where it couldn't get enough sunlight to recharge its batteries, and after only a few hours, it went dark. But before it went dark, it was able to return these remarkable images from the surface of a comet. We can see the dark, icy, rocky material that makes up this amazing world. Recently, the Philae lander woke back up again. As the comet gets closer to the sun, it actually got enough sunlight on its solar cells to be able to recharge its batteries and turn its radio back on. Although it's been in and out, and it's not clear if it will be able to get all of the data from it, the tiny amounts of data that have been returned have revealed that comets are individual and wonderful worlds all themselves. We live in a remarkable solar system in a time when our robotic spacecraft have visited many of the bodies in the solar system, certainly every major class of bodies, the planets, the dwarf planets, the giant moons, even asteroids and comets have been visited by the robotic emissaries of mankind. We've only begun the exploration of our solar system. It's a place of a vast number of wonders, wonders that we hopefully will continue to explore for many generations to come.